Recording in progress.
So we will start the chapter 8 review. Chapter 8 is on chemical composition. And so the first question is asking what is the difference between atomic mass and molar mass of an element. And so if we look at the periodic table, that's where you will find the atomic mass. And notice how in yellow here, it shows how the average atomic mass is shown below the name of the elements. And so, for example, for carbon, it's going to be 12.01. You know, oxygen is 16.00. And so the atomic mass is in units of atomic mass unit, AMU. And so it's an average because atoms have isotopes. You know that for an element, you have different isotopes typically for an element. And the isotopes have different mass due to the fact that they have different number of neutrons. And so when you find a sample of carbon, for example, in the ground, and you analyze it, there is more carbon 12 than carbon 13 or carbon 14. You know, carbon 13 and carbon 14 are two other different isotopes of carbon. But when you take the mass of, you know, when you take the average atomic mass of carbon, then it's going to be an average of the mass of the different isotopes of carbon, you know, carbon 12 plus carbon 13 plus carbon 14. But because carbon mainly contains the isotope carbon 12, so that's why the mass is close to 12 atomic mass unit for carbon, for example. So that's what is the atomic mass. And so let me show that. So the atomic mass of an element is the mass of one atom, or the average mass of one atom of in units of atomic mass unit. And so for the carbon 12, so for the carbon, it has an atomic mass of 12.01, and I explained that the reason is because the carbon 12 isotope is the most abundant, and so the average atomic mass for carbon will be the mass of carbon 12. So now, what is the molar mass of an element? The molar mass of an element, so here the key word is molar. The fact that it's molar means it's the mass of 1 mole. It's the mass of 1 mole and 1 mole of atoms, because here we're talking about an element. So it's 1 mole of atoms of that element. And remember how 1 mole is 6.022 10 to the 23rd atoms. So that means the molar mass is the mass of this many atoms, you know, of the element you're looking at. So, and it happens that the molar mass of all the elements correspond to the same number in atomic mass unit. It's the same number. So for example, the molar mass of carbon is 12.01, but what changes is the unit. It's in grams per mole. So same number as the atomic mass, but with a different unit. So the molar mass will be given in grams per mole, while the atomic mass will be given in AMU, atomic mass unit. And of course, the atomic mass unit refers to the mass of one atom, or the average mass of one atom. And the molar mass is the mass of 1 mole of these atoms. So it's the same principle with the formula mass. So the formula mass of a compound. So this time we are talking about a compound. And so the mass of one formula is obtained by taking the mass of, you know, the atomic mass of each atom that are in the formula, multiplied by the number of atoms you have in that formula. And so it's going to be also in units of AMU. The formula mass will be given in units of AMU because it's just for one formula. For example, the formula mass of CO2 is 12.01 gram, not gram, AMU plus 16.00 for the oxygen times 2, because you have 2 oxygens per carbon in that formula. And so it's 44.01 AMU. So it's the mass of one formula, right? And it's in units of AMU. And then the molar mass of a compound, it's again going to be the same number, except that it's going to be in grams per mole. So it's in grams per mole. And so it's not the mass of one formula anymore, it's the mass of one mole. It's 1 mole of these formulas or molecules. Notice how we call molecules the molecular compound and formula units when we are talking about ionic compound. So we don't say molecules when, for example, for NaCl, which is an ionic compound, we don't call NaCl a molecule. We call that formula units of NaCl. So it's the mass of 1 mole of molecules of CO2, for example, here, and it's in grams per mole. So that answers question 1. Question 2. So let me. Question 2. How many moles of hydrogen are in 6.33 moles of NH3? So NH3 is ammonia. That's one molecule like water that has a common name that you need to know by heart. And so NH3 is ammonia. So we have this number of moles of ammonia, and we want to know how many moles of just the atom of hydrogen there. So the concept map will look like this. We start with moles of NH3, and we want moles of H only. So H is part of NH3. And so this is what we call a mole-to-mole conversion that we need to do here. It's a mole-to-mole conversion. And because H is part of the formula of NH3, you only need the formula, to find how many H you have per NH3. And so if you look at the formula, it tells you that there are 3 atoms of H in 1 molecule of NH3, right? If you look at 1 molecule of NH3, you have 3 atoms of H and 1 nitrogen, right? 1 nitrogen surrounded by 3 hydrogens. So this ratio of 3 atoms of H per molecule of NH3 can be written in number of moles, because in chemistry, dealing with just 1 molecule and 3 atoms is not realistic. So the mole, the concept of the mole has been, established to give more realistic masses and, samples that you can see. And so typically we work in moles. And so if you multiply, these 3 atoms by the Avogadro number, so that means you will have 3 moles of H, right? So if we write this in number of moles, there is 3 moles of atoms of H in 1 mole of molecules of NH3, right? You just multiply everything by moles. But the ratio is the same, 3 moles of H in 1 mole of NH3. Now, because we need to do some calculations, so how do we write this mathematically? We write it like this. 3 moles of H equals 1 moles of NH3. So of course it's not equal. Here it's equivalent, or you can read it as is contained in 1 mole. So 3 moles of H are contained in 1 mole of NH3, right? But it's helpful to write it as a mathematical equality like that, to see that it's an equality that you can use as a conversion factor. So we can use this now, this equality as a conversion factor, which means, write it as a ratio, either 3 moles of H over 1 mole of NH3, or, because there is always 2 conversion factors per equality, or 1 mole of NH3 over 3 moles of H. And so here, because we are starting with moles of NH3, it's our given amount here. So always start the calculations with the given amount of 6.33 moles of NH3. and then write this equality as your conversion factor. So let's do this, and I've prepared here the given amount. Always start the calculation with the given amount, and the given amount is in the numerator, even though here it looks like in between. It's always in the numerator, right? You can also have a line and then a 1 in the denominator. So as always, the units are our guide to know what to do next. And here we have moles of NH3 as the given amount. And so we want to cancel that unit because in the end, we want moles of H, not moles of NH3. So you want to cancel the units of moles of NH3. So you want them in the denominator in the conversion factor. And the number of moles we have is 1 mole of NH3 for 3 moles of H. So what goes on top is going to be the 3 moles of H. And so this way, the moles of NH3 cancel. And I could show that briefly here. Hold on.
Recording in progress.
So the units of moles of NH3 cancel, and in the calculator you do 6.33 times 3, and divided by 1 is not necessary. So it's 18.99. No, need to be inside here. 18.99, and the unit will be moles of H, which is what you want, right? So that calculates the number of moles of H in 6.33 moles of NH3.
Recording in progress.
So question 3, how many grams of carbon dioxide are in 0.220 moles of CO2? So we have moles of CO2, and we are looking for grams of carbon dioxide. So carbon dioxide is CO2. So we are dealing with the same substance here. And we have moles of it, and we want to know grams of carbon dioxide. So let's look at the concept map. The concept map looks like this. You start with moles of CO2, and you want to change that to grams of CO2. And if you remember above, we saw that the molar mass was what relates grams to moles, right? Because it's the number of grams for 1 mole of the molecule of CO2 here. And actually it's even CO2. So we have everything there already calculated for us. But let me show how we do this. Well, actually I showed it here, but I'll show it here. So how do we calculate the molar mass of a molecule? So you take, so for each atom in there, you take their molar mass. So for carbon, it's 12.01 gram. And you multiply by 1 because there is only 1 carbon in that formula. Then you take 2 times, because you have 2 oxygen per formula. So 2 times the molar mass of oxygen. And that's 16.00 grams. And these numbers, they come from the periodic table, right? 16.00 for oxygen and 12.01 for carbon. And then you add them together. And for carbon dioxide here, it's 44.01 grams per mole of CO2. So let me say that here, this is an addition. And so if you use the periodic table I provide, it almost always has 2 sig figs or 2 decimal, I mean, 2 decimal in the molar masses. So you should always give 2 decimal to your molar masses, right? Because when you add, you need to keep the same number of decimal places as you have in your numbers, and they both have 2 decimals. Okay, so this is the molar mass. Mathematically, the molar mass can be written as an equality because it's made of 2 units, right? It's grams per mole. And per mole means that in 1 mole of CO2, you have 44.01 grams of CO2. So mathematically, we like to rewrite the molar mass like this because it shows the equality, you know, and from the equality, you can write the conversion factors. So 1 mole of CO2 is 44.01 grams of CO2. So you see that then we can change the moles of CO2 into grams of CO2 because we have a relationship, a direct relationship between the two. Always start the calculation with the given amount. And so that means we will start with 0.22 moles of CO2, which is what was given here in the text. This is in the numerator. Again, it's like having a line under and a 1 in the denominator. And so because you have moles of CO2 in your given amount here in the numerator, you want to cancel that unit. And so you want to have your conversion factor such that the moles of CO2 will be in the denominator. And here the molar mass gives 44.01 grams per mole. So 44.01 grams of CO2 will go on top. Here, no, not this one, 2. Oh, okay. Okay, so we have our moles of CO2 on the bottom and then the grams of CO2 on top. And so we see that this way we can cancel the units. And let me, oh, no, I cannot. Okay. Oh, I see now. And so let's just unit. So you can see moles of CO2 cancels. And so then we are ready to do the calculation in the calculator, and it's going to be 0.220. Oh, that makes me think I forgot about sig figs in the previous example. So let's write the answer here, 9.6822, and that's the calculator answer. So these things need to move together. Okay. So let's think about sig figs here. How many sig figs in the given amount? We have 3, the 2, and the 0 to the right. The molar masses, so the 1, you know, per mole will always be exact, so doesn't limit. And so the molar mass can limit, but typically, usually you have enough digits in the molar mass. So here we have 4 sig figs in the molar mass, but only 3 in the given amount. So we need to keep 3. So that means we will keep the 9.68. What comes after the 8 is a 2, so we just keep the 8 like that. We round down. So that's the final answer for this question, 9.68 grams of CO2 per 0.22 moles of CO2. So I want to rectify the answer above here because I didn't pay attention to sig figs there. And so here, the 3 moles of H per mole of NH3 are all exact numbers, right? It's whole numbers from counting number of atoms per molecule. So they are not limiting. So the limiting measurement is the number of moles, the starting number here. So we have 3 sig figs in 6.33. So we need to keep 3 sig figs, and it's going to be 18.9. However, what comes after the 9 is another 9. So that is going to be rounded to 19.0 moles of H. So that's more correct for the answer to question 2.
Recording in progress.
So question 4 now. A piece of chalk, which is made of calcium carbonate, is used to write the Avogadro number in decimal notation on a board, on a blackboard. So you write 6, 0, 2, 2, and then 20 zeros, because in decimal notation means you don't use the scientific notation, but you write all the zeros. So 20 zeros plus the 6, 0, 2, 2. And so that's a lot of writing on the blackboard. And so the piece of chalk had a mass of 10.7 grams before the writing. And now it has a mass of 10.2 grams after the writing. So that means you have left the difference in mass here is left on the board. It's showing up on the board and showing you the Avogadro number written in decimal notation. And so the question is, how many formula units of calcium carbonate have been deposited on the blackboard? So notice here, we don't ask how many molecules of calcium carbonate, because that's not proper. We don't talk about molecules when it's an ionic compound. Here, calcium carbonate is made of a metal and a non-metal, so that's an ionic compound. And so then we talk about formula units. So how many formula units of calcium carbonate are left on the board? So let's write down the formula of calcium carbonate first. We need to know what we're talking about. So calcium here is in group 2A, so it's going to be a 2+ ion. And then carbonate, maybe you remember here, carbonate is CO3 -2. So together, 2 positive charges, 2 negative charges. So you need only one atom of, not one ion of each, and that will make a neutral formula. So then you just remove the charges and it's a CaCO3. So that's calcium carbonate. Next, we need to find out the mass, because that's the only given here, the mass of calcium carbonate that is left on the board. And so you're going to take the mass of before the writing and then remove the mass after the writing. And so the difference in mass is 0.5, right? Because you do 10.7 minus 10.2, and that's a difference of 0.5. We keep 1 decimal because both numbers had 1 decimal. So we have 0.5 grams of calcium carbonate, left on the board, on the blackboard. And we want to know how many formula units of that are in those 0.5 grams. So the formula units means you will need to change to get to formula units, that you have to go through moles, right? Because formula units only show up in the definition of the mole. Definition of the mole. 1 mole of CaCO3 units is 6.022 10 to the 23rd formula units of CaCO3, right? You always want to adapt the definition of the mole and use the substance you have. And so here, 1 mole of calcium carbonate units is 6.022 10 to the 23rd formula units of calcium carbonate. So this will allow you to find the formula units. However, it's related to moles, and you have grams. So that means you will need the molar mass of calcium carbonate to relate the grams to the moles. So we need the molar mass of calcium carbonate. And so for this, you take the mass of calcium. So let's look at the periodic table. It's a 40.08 for calcium, 12.01 for carbon, and 16.00 for oxygen. So then you do 1 time the 40.08 grams for calcium, plus 1 time the mass of carbon, so 12.01 gram, plus 3 times the molar mass of oxygen, so 3 times 16 grams. And that's a total of 100.09 grams per mole. So be careful, it's not 100, because each of the molar masses come with decimals. You need to calculate up to the 2 decimals, right? So to be correct, you want to write 16.00 and not just 16. So the molar mass of calcium carbonate is 100.09 grams per mole. So as always, we want to rewrite this mathematically as an equality. And so the molar mass written as an equality will look like this. It's 1 mole of CaCO3 equals 100.09 grams of CaCO3. So we are ready to write the concept map now. The concept map will look like this. So we start with grams of CaCO3 because that's what is given here with this, difference of mass from the chalk. So we will start from that, then change them to moles using the molar mass of CaCO3. And then once we have the moles, we can change the moles to formula units using the definition of the mole. So that's the concept map. So that those arrows here, 2 arrows, tell you you have 2 conversion factors. And so that's those 2 equalities we just saw here that will be used as conversion factors. So let's start the calculation. So you always want to start the calculation with the given amount. And here the given amount is 0.5 grams of calcium carbonate. So have it in the numerator always. So it's like having a line under and a 1 in the denominator. So because you start with grams of CaCO3, that means you want to cancel that unit. And so that means you want the gram of CaCO3 in the denominator of the first conversion factor, which means you will use this equality here because it has the grams. And it's 100.09 grams. And that's for 1 mole of CaCO3. So notice how the abbreviation of mole is MOL, or you can write mole MOLE like it should be. But be careful, officially the abbreviation for mole is MOL, this does not mean molecules, be careful. So 1 mole of CaCO3 has this mass. So here at that point, we can cancel the units of grams of CaCO3, right? And we have moles of CaCO3. So then the second conversion factor should be written such that we cancel the moles of CaCO3, right? The units here should not stay because that's not what we are looking for. We are looking for formula units. And the definition of the mole here tells you that for 1 mole, so it's 1 mole in the denominator, we have 6.022 formula units of CaCO3. Let's see if we can have this in there. I don't know. No. So 6.022 times, well, I'll do it. Oh, sorry, I'm in the wrong place. Times 10 to the 23. 23. The 10 here. And the units of that are formula, or, I will just write CaCO3 units. Because, those units can be long, and it's okay to write just CaCO3 units. So this is 4 grams. And this way you can see that the units of moles of CaCO3 cancels, right? CaCO3. And we're left with units of calcium carbonate, which is what we want, right? So let's write CaCO3. Oh, not inside anymore. Oh, CaCO. Oh, 3 units. So that's going to be the unit left over, right? Once you have canceled the grams and the moles of CaCO3. So in the calculator, you do 0.5. So I like to multiply all numerators together. So 0.5 times 1 is not necessary, times 6.022. And then make sure you use the scientific notation here. So use the second function of the x minus 1 key if you use the ti 30x 2x. So I have the capital E show up and then 23 for the exponent. So that's the numerator, and then divide by every denominator. So divide by 100.09 here. The calculator answer is 0.30, no, sorry, 3.008. I think that's plenty digits, right? Let's see how many sig figs we need to keep here. So every 1 mole are exact, right? Those 1 moles are exact. They do not limit the number of sig figs. The Avogadro number here has 4 sig figs. The molar mass has 5. And the given amount has only 1 sig fig. So we need to keep only 1 sig fig. And that's going to be just the 3. So that's a 3. Wait, I'm sorry. That's not possible, what I wrote there. So I forgot the times, and you see how it is easy to forget. So I forgot the times 10 to the, my calculator is showing an exponent of 21. So 3.008 times 10 to the 21 calcium carbonate unit. And I was going to simplify that to 3 times 10 to the 21 units of calcium carbonate. Okay, so be very careful because the calculator cannot show this kind of number without using the scientific notation. So it shows you the decimal part, but it's up to you to look on the right side of the screen of your calculator and see that there is a times 10 to the 21 there. So do not forget to report that because otherwise your value will be completely wrong. And so that's the value, 3 times 10 to the 21 calcium carbonate units, you know, and that's what you have on the board when you leave 0.5 grams of chalk on the board. So whenever you're calculating a number of formula units or number of atoms or number of molecules, always expect a large number close to the Avogadro number. So you should always have a number with the scientific notation, and 10 to the power of, you know, something around 23. Otherwise, if you do not have that, then there's something wrong in your calculation.
Recording in progress.
So let's go over question 5 now. And so notice how I say it's similar to homework 8 question 14 or 17. Similar doesn't mean it's exactly the same. So please adapt when you are doing question 14 or 17. But there is some similarities to it. So this example here can help you solve the homework 8. So calculate the number of oxygen atoms in 21.5 grams of sodium sulfate. We need number of oxygen atoms, right? So see atoms as particles, right? And this should ring the bell of the Avogadro number, because the Avogadro number or the definition of the mole is giving you the number of particles for 1 mole. That's the only way to get the number of particles is to go through moles. So that tells you will need to use moles to get to atoms. And it's atoms of oxygen, so it's not the compound, it's just one element out of the compound. And so that tells you will need to use the formula, because when you're asked about oxygen atoms out of sodium sulfate, oxygen is part of the sodium sulfate. And so you will need to use the formula to know how many oxygens you have per formula. And the starting amount is 21.5 grams of sodium sulfate. So it's grams, and we said we need to go through moles, so we will need the molar mass of sodium sulfate. So first, let's write the formula of sodium sulfate. Sodium, here, atomic number 11, is in group 1A, so it likes to make the Na plus ion, right, +1. Sulfate is a polyatomic ion and is just below the sulfite here, and here it is SO4 negative 2. So SO4 negative 2. So you have 2 negative charges for 1 positive charge. So the sodium sulfate will look like this. You take the charge, the 2 from the charge of the sulfate, and that becomes a subscript for sodium. And then the sodium has only 1 charge, so that means you will need only 1 sulfate. And it makes sense here that you need 2 Na plus to cancel the 2 negative charges on the sulfate. So the formula is Na2SO4. That's a sodium sulfate. So next, let's see, we need the molar mass of this compound, right? Because we have grams and we will need to go to moles. So the molar mass of Na2SO4, so for this, you take 2 times the molar mass of sodium. So sodium here, 22.99 grams per mole. And we have the sulfur, 32.07. And then the oxygen again, 16.00. So you take 2 times the molar mass of sodium because you have 2 sodiums per formula. Then 1 time the molar mass of sulfur, and it's 32.07 grams. And then 4 times the molar mass of oxygen because you have 4 oxygen in that formula. Add all of this together. Notice how they each have 2 decimal. So you need to keep 2 decimal in the end. And so it's 142.05 grams per mole of Na2SO4. Because we are doing, using this as a conversion factor, I like to write it mathematically as an equality. So let's show how we write this as an equality. 1 mole of Na2SO4 is 142.05 grams, right? And actually, to be correct, fully correct, I need to repeat that it's grams of Na2SO4. So that's going to be one of the equality that will allow you to change the grams you start with here to moles of the whole compound, Na2SO4. Then from the mole of the compound, we need to extract just oxygen. So we will need to use the formula itself. And the formula shows you there is a subscript 4 for oxygen. So that tells you there is 4 oxygens per Na2SO4. And the way we can write this is that 1 mole, so multiplying by mole, by the Avogadro number, we get a number of moles. So in one formula, we have 4 atoms, but in 1 mole of this formula here, we have 4 moles of oxygen, right? You just add mole, to formula and atoms. So that was obtained from the formula, right? That was obtained from the formula.
Recording in progress.
So once you have the moles of oxygen, from the moles of the compound, then you can calculate the number of atoms, the number of particles per mole. And for this, you use the definition of the mole that says 1 mole of oxygen is equal to 6.022 10 to the 23rd atoms of oxygen, right? So you change particles by atoms. Here we are talking about atoms. So that's the number of atoms per mole of oxygen. And so that would lead to the answer here because we are asking for number of oxygens. So let's show the concept map because it's a bit long here. Here, the concept map shows that we start with grams of Na2SO4. From the molar mass, we can get the number of moles of Na2SO4. And from the moles of the compound, we extract the moles of just oxygen. And then from the moles of oxygen, we can obtain the atoms of oxygen using the Avogadro number. So you can see that there is 3 arrows, which tells you have 3 conversion factors. The last one here is the definition of the mole. The middle one here is, using the formula to find the number of oxygen per formula. And then the first one is using the molar mass of the compound. So let's start the calculation. And so as always, you start the calculation with the given amount. The given amount here is 21.5 grams of sodium sulfate, the whole thing here. As always, this is in the numerator, even though it shows up here in the middle, it is like having a line under and a 1 in the denominator. So please see this as the numerator. So we want to multiply by the first conversion factor that will change the grams of sodium sulfate to moles of sodium sulfate. So this is the molar mass we need now. And because we have grams of sodium sulfate in the numerator, we want grams of sodium sulfate in the denominator. And the number that comes with the gram is 142.05, right? It's this. And that's for 1 mole. So 1 mole will go on top. 1 mole of Na2SO4 goes on top. So this way we can cancel the grams of Na2SO4. In the next conversion factor, we want to cancel the units of moles of Na2SO4. So you want this unit to be in the denominator so that you can cancel the unit. And what comes with the moles of Na2SO4 is going to be 1 mole. And remember how here, the moles of Na2SO4 will be changed into moles of oxygen. So we will use this equality here. And so it's 1 mole of Na2SO4 contains 4 moles of O, just O, 4 moles of the oxygen atom. So we cancel moles of sodium sulfate, and we're left with moles of oxygen, which we want to cancel in the next step. So you want the moles of oxygen on the bottom of the conversion factor that comes after. And that's going to be 1 mole of oxygen here, because we will use the definition of the mole to get the number of atoms. And so on top, it's going to be 6.022 times 10 to the 23rd. And the particles here are atoms of oxygen. Let me make this smaller so that it stays in one line, because it is important to keep everything in one line to see how unit cancels. So let's show how unit cancels. So we have the, let me use different colors. So grams of Na2SO4 here cancel. Then we have moles of Na2SO4 cancels, one on the numerator, one in the denominator. And then the third one is moles of oxygen that will cancel. And we're left with atoms of oxygen, which is exactly what we want. The unit we want, right? The question was asking for number of atoms of oxygen. So let's do the calculation in the calculator. So you do 21.5. I like to multiply all numerators together first and then divide by each denominator. So here, multiply by 1 mole of sodium sulfate is not necessary. Multiply by 4 moles of O and multiply by the Avogadro number, 6.022. A second function to have the EE key and then write the exponent 23. Because you use the scientific notation, there's no need for parentheses here. And then divided by the only denominator that matters here is 142.05 grams of sodium sulfate equals. And so that's the calculator answer. 3.6458 times 10 to the 23rd. Again, we are calculating particles, so we expect a large number and we expect to need the scientific notation here, right? So 10 to the 23rd is making sense. And the unit is atoms of oxygen, because that was the unit left over after canceling. So how do we run this? We have, so as always, the 1 moles are always exact numbers, not limiting. The 4 moles of oxygen per mole of Na2SO4 is also exact. You know, you're counting number of oxygens per formula. The 1 mole here is exact. So the Avogadro number has 4 sig figs. The molar mass has 5 sig figs. And the given amount has 3 sig figs. So we need to keep 3 sig figs. So we keep the 3.64. What comes after the 4 is a 5. So the 4 will become a 5. You round up. And then you rewrite times 10 to the 23rd atoms of oxygen. And so does it make sense? If we look at the mass, it's much smaller than 1 mole. But we have 4 atoms of oxygen per formula. So that's why it's still less than 1 mole, but half of it here. And so that solves question 5 here.